Okay, so today I want to talk more about the homotopy theory of stratified spaces, which isn't something I talked so much about last time. So let me, because there were a lot of things that were done last time, let me sort of recap some things. And then I'll also say a little bit about some questions related to the theorem from last time before I get started sort of attacking the stuff for today. So last time, we did a number of things. So the first thing was that we introduced an adjunction. Okay, when I say the first thing, it's not in this order at all, but the first thing that I want to remind you of is that we introduced this adjunction from simplicial sets over the nerve of the poset to topological spaces over the poset in this Alexandrov topology. And so the left adjoint of this adjunction was you realize and then you post-compose with this just completely canonical stratification of the realization of the nerve of a poset provided by these natural stratifications of n simplices that look like this. And then there was a sort of pullback of the singular simplicial set called Sing P. And this guy, Sing P, was supposed to play the role of this exit path infinity category, but it wasn't always an infinity category. But what we did was we defined a class of what we called conically stratified spaces. With the property that if T down to P is conically stratified, then this Sing P of T is a quasi-category. And in that situation, I like to call this just, in this situation, I'll just call this exit P of T, because that's what it's playing the role of. And so some examples of these conically stratified spaces, well, so examples include what are called topologically stratified spaces. These are something considered by Goretzky and McPherson that it's really just a specific class of conically stratified spaces stratified over over brackets n, and you require some things to look like Euclidean spaces in the conical condition. But importantly, a particular example of this is by work of Mather and Tom, these things called Whitney stratified spaces. So I don't really want to go into what this is. I mean, it's a sort of analytic condition that Whitney talked about that I think probably David will talk a bit more about these sorts of regularity conditions. But basically it's the somehow like the most classical example of stratified spaces that people considered. And the other thing to note is that in this setting, this functor exit P of T to the nerve of P that's just sending the point to the the element of the poset that it lies over is conservative. and then the thing that I ended with was explaining a version of monodromy for constructible sheaves. And what was that? And this is where I want to try to answer a few questions from last time as well. So it was this theorem in this form due to Lurie that says, so T will be a paracompact topological space. Locally singular shape. And this really just meant that the monodromy theorem that Clark talked about in the first talk works. And P will be a poset satisfying the ascending chain condition, which I'll just write as ACC. I'm not going to say Noetherian or Artinian because I think not everyone agrees on this, so I'm just going to say that. And if you have a conical stratification, then there's an equivalence on the one hand, you have functors out of this exit path category to the infinity category of spaces. And then on the other hand, you have sheaves that are constructible with respect to the stratification. And how's this equivalence work? Well, by straightening on straightening, this is equivalent to left fibrations over this exit P of T. And there's a functor that I'll define that way that's an equivalence. And it's going to send a Y over this exit path category that's a left fibration to there'll be a pre-sheaf sends an open subset to functors over exit P of T from exit P of U to Y. And the thing to note, as Ezra asked last time, is that this conical condition, somehow it's kind of made to be local. So if you have an open subset of a conically stratified space, then it's also conically stratified. That's an easy thing to check. So this formula actually makes sense. And another thing to note is that in this setting, well, if I invert everything, which I'm just writing as B, in the exit path infinity category, that this is equivalent to the underlying homotopy type of that topological space. Okay, and so something I didn't mention last time, but I wanted to mention this time.
Hey, Peter, can I interrupt real quick?
Yeah.
So here you've got functors from exit P over U to Y over exit P of T.
Yes.
And one thing that you mentioned last time is that that's actually just a space. It looks like it's going to be an infinity category.
Yeah.
But in fact, it turns out that it's just a space.
Yeah. So well, yeah, let me not fill the thing that's up there. So it's actually equivalent to the space. And the important thing to note is that, yeah, in this setting, all of the strata, so I mean, these things are all over P. And all of the strata are Kahn complexes. So that was the conservativity of this functor. And then this is a left vibration. So this this composite's also going to have that property. And the thing to notice is, that if you're over your post set and you have some, two functors over the post set, but then since all the strata are Kahn, if you had a natural transformation, somehow it's all in the sort of strata direction.
Yeah.
So then it's going to be an equivalence actually. So yeah, that's very important because otherwise, I mean, this looks like it's actually an infinity category, but all morphisms are invertible. So it actually makes sense. Yeah. So yeah, that's a very.
I have a quick question just to kind of verify that I'm following. So cons P of T, that is always an infinity topos, right? Like with no assumptions whatsoever. And then
yes.
Let's see. Is that? I want to make sure that's true. I'm slightly worried that.
I think that's right because you can define it in terms of an iterated pullback of morphisms of topoi.
Right.
Yeah.
Right. Yeah. Yeah, and I guess so. Part of the thing here, right, is that without some collection of these conditions that maybe is not completely easy to identify which ones are absolutely necessary for this. This side may not be hypercomplete. So part of these conditions are guaranteeing that this is hypercomplete because you're saying it has to be equivalent to some hypercomplete thing.
Yeah, functor categories are always hypercomplete, aren't they? So
yeah. They're even Postnikov complete. So everything's the limit of its Postnikov tower because that's true in spaces. But in general, that might not be true here. So I mean that's part of this ascending chain condition, and paracompactness. But it's the proof's a bit complicated, so it's a little hard to identify exactly what's like the minimal set of conditions for everything to be true. But
make a comment on that point. So last time we mentioned how once you know the infinity category of constructible sheaves, then the completely compact objects they're in, or the atomic objects, is the exit path category.
Yeah.
And then you automatically then get an adjunction between pre-sheaves and the exit path category and constructible sheaves. And I find it from afar surprising that this topos of constructible sheaves would be free in the sense that it's the free co-completion of something. I see no like otherwise conceptual reason for that other than it's just true.
Yeah, no, it's pretty surprising. And I mean, well, I guess so. Something something that we'll see much later in the algebra geometric setting is, I mean, and somehow this is kind of already in some sense appeared with the shape theory setting. Like in the algebra geometric setting, what's going to happen is, it's not an actual functor category. It's functors out of some pro category. So it's some inverse limit of functor categories, but it's no longer actually just a functor category. So somehow it's kind of almost one, but yeah. So this sort of very surprising thing doesn't quite happen.
Well, or you have to do something creative, like pass to the pycnotic setting in order to get your freeness back.
And then you get your freeness back.
Your freedom returns to you.
You're free, yeah. something that we would all like in these times. So here's one consequence of this that I wanted to mention, that I think is quite compelling. That so I mean, if you don't know what intersection homology is, it's not really important. But the important thing is an invariant of certain types of stratified spaces, essentially sort of, you know, singular manifolds with stratifications that were considered by Goretzky-McPherson. But the upshot is that the intersection homology of a topologically stratified space, this is just the setting in which this is defined. So it's some particular type of conically stratified space over a linearly ordered finite poset. It only depends on what I'm gonna call the stratified homotopy type that's this exit path category. And let me just make a very small comment on this. So yeah, how can you see this? Well, the point is that there's a definition of this intersection homology, you know, as you know, some homology coming from a constructible sheaf, and that constructible sheaf only depends, you know, you can define it only knowing what this exit path category is. So so even some, you know, very important things that people considered, well, somewhat classically, they only depend on this exit path category. So, oh, this P should be a bracket set. So what that suggests, you know, along with all this other stuff, it suggests that we should consider stratified homotopy types as the exact sort of categorical object that this exit path thing is, infinity categories with conservative functor to a poset. And okay, so essentially the point of today's talk will be to show, I mean, you can say what this infinity category is without any reference to a topological space ever. But the point will be to explain why this is actually equivalent to a homotopy theory of stratified topological spaces. But there's one thing that I want to do before that related to this this theorem is I want to just say a few small words on a question that Jay asked last time. So this is going to be a hopefully pretty brief digression that's related to this theorem. So there were a couple, yeah, there were a couple.
Sorry, before we get in, could I just ask about that remark or observation, whatever it was?
Yeah.
I learned about intersection homology like ages ago, but I feel like I recall it depending on the local dimensions of strata and so on. Is that right?
Well,
and if so, how is that avoided?
Yeah, so I mean, for this, I'm thinking, so there are various definitions of intersection homology. So usually there's this first one that you construct this like complex that, you know, using actual like very like, topological things about your space. But the point is that Deligne had this idea that turned out to be right, not surprisingly, that there was a way of defining intersection homology that didn't use all of this like very sort of very fine geometry. And essentially what he said is that you define it as a certain constructible sheaf. And what you do is on the open stratum, so the piece over N, you take some locally constant sheaf, even just some constant sheaf, say at an abelian group. And then you push it forward to the piece that lives over N minus 1 in N. And then you do some truncation, and then you push it forward, and then you do some truncation, and you keep on doing that. And specifically what truncation you do depends on the choice of what's called a perversity. But the important point is that you're ending up with a constructible sheaf in the end, and you only start with like a local system on the open stratum. So that's just something that depends on the underlying homotopy type of the open stratum. And you do operations that remain in the world of constructible sheaves.
So maybe pursuant to what Aaron was saying a little bit is that this perversity function, the thing that defines a T structure on the category of constructible sheaves, a spectra or whatever, that perversity function is again something that's expressible exclusively in the terms of the exit path category.
So maybe the difference between expressible and like could be defined if somebody only handed you that. If I handed you a space and told you that it was the underlying space of a manifold, of course, you're not going to be able to say what dimension it is, and you're not going to be able to,
but
like, you don't have Poincare duality for free, I guess.
You shouldn't be too addicted to the idea of dimension, though. I mean, a perversity is quite a general thing.
Yeah, and so, right, I mean, part of this is like, there's one perversity that's usually chosen, but there are different options. And I mean, yeah, so if you work in sort of the amount of generality that you're allowed to, it really only depends on this guy.
Okay, but so maybe having like the correct coefficient system, for an ordinary manifold, that has to do with the tangent bundle and orientations of that. If you want Poincare duality, maybe there is there extra data in the perversity and the like correct choice of local system for getting Poincare duality?
I mean, you have to choose a suitable perversity to have something like that happen. Sure.
Yeah. So yeah, certainly you have to choose a suitable perversity, but
the perversity essentially report the just like you're getting at the dimension of each strata, so that the dualizing complex, which is also constructible, is aligned with that perversity.
Okay, thanks. Yeah, I feel like that's the sort of thing I was.
Yeah. So
we don't have to go down this too far.
Yeah. So I guess the point is, I mean, you're allowed to. I mean, perversities are very general, and you're allowed to pick any one for this, and sort of, you're just, if you're given this sort of singular manifold, there's a one that you can in particular define. So that it chooses one of them for you. Okay, but
can I ask the question? So are we going to look at perversities in this setting at all, or is this just a incidental remark?
This is at the moment. This is an incidental remark.
I was hoping to talk about perversities, however. I have so my. This is just as a prelude. I mean, I have this idea that for a general post set, there should be a suitable notion of a perversity, and that suitable notion should be it's not in general, it will not in general give rise to a T structure, but rather a more general kind of filtration, which actually I learned from Tomer you can re-express as a family of T structures. But that filtration is still interesting. And for example, I claim that it gives you the slice filtration when you think about your poset being the category of conjugacy classes of subgroups of a fixed finite group, say. So that is something that I was hoping to talk about later, but that's later.
Yeah. At the moment, I don't want to talk more about this. This is just a sort of interesting remark. But the thing I did want to issue a few warnings related to some questions asked about this last time. So the first one is to note. So Jay asked some question about do we know that about various things living in here, like do we know that T equals P is an example of this sort of thing? And there are sort of two small warnings to issue about this. I mean, in a lot of cases, things are going to be okay. It's always the case that exit P of P is just the nerve of P, because this seeing P construction, right? It's a right adjoint. It preserves this terminal object. But there are a few things that I thought about a little bit that are slightly cumbersome. So the first thing to note is that these posets provide an example of something that's not usually conically stratified. So posets are not usually, basically ever, conically stratified. And the example to look at is just the poset that I write brackets 1, 0 is less than 1. So if you look at the sort of condition you need, basically you see that you need to be able to embed like, a half open interval in the real line into this guy. But I mean, you can't do that, it has 2 points. But that's okay. The other thing to note is that, so that's sort of warning 1. And warning 2, I think more pursuant maybe to Jay's question, is that posets satisfying the ascending chain condition need not be paracompact. And so, I mean, here's an example of a poset that satisfies the ascending chain condition and the descending chain condition, for example. So, I mean, you take the specialization poset of spec Z. So, I mean, you take, a countable collection of elements, and then you adjoin a new biggest element. So you can take like N with the discrete topology or discrete poset structure, and you adjoin a new biggest element. Yeah, so this guy is not paracompact because you can take the cover that consists of everything bigger than 0, 1, all of these points, but there's no locally finite refinement of that around the point infinity. And it's also, I mean, it actually seems to be kind of annoying to characterize paracompact posets. So, I mean, something that you might say is, well, in this example, there are infinitely many points less than some element. Maybe that's something that is bad as well. Like, but you can actually come up with other examples that where every point has finitely many elements less than it, but it's still not paracompact. So one example of that, but it doesn't satisfy the ascending chain condition. So it just sort of different example is if you have a poset that looks like this. So my arrows go in the less than direction. So you continue like this, keep on having these elements like this. And this is also not paracompact. But then there are also posets that, you know, that do satisfy these conditions. I don't know. It seems a bit weird. So I mean, there's a poset that is paracompact, but it doesn't satisfy this down finiteness condition. Namely, I mean, you take like the negative integers and adjoin a new minimal element. So I don't know, it seems a bit annoying to characterize these, but I just wanted to, you know, sort of tie that up. Okay, but that was it. That was really a digression. So now I want to get into, you know, actually talking about something new. So what do I want to do for the rest of today? I want to sort of state what I'll call stratified homotopy hypothesis. So this is going to be an equivalence between some purely homotopical objects, which are infinity categories with a conservative functor to a poset, and some things that actually have to do with stratified topological spaces. And then I want to give a sort of proof overview of this result. And so this will, for example, we'll talk about the subdivisional model for stratified spaces that some people asked about questions last time, and also some various model structures. And so the sort of references for this, well, so yeah, the thing that I'm mainly going to be talking about is my paper that's called On the Homotopy Theory of Stratified Spaces. That's mine. And then some other stuff that's relevant that I'll say a tiny amount about. And then I think on Friday, David's going to tell us a lot about is David's paper with John Francis and Nick Rosenblum called a Stratified Homotopy Hypothesis. Okay, so yeah, so what's the point? Well, so the question is, what is really the homotopy theory of p-stratified spaces? And what we want, sort of in an ideal world, is an equivalence. Well, I mean, we saw various things, for example, this intersection homology and sort of constructible sheaves that only depend on this exit path category. So what we want is an equivalence between some homotopy theory of P stratified topological spaces on the one hand, and on the other hand, well, so it should be something that's given by this exit path construction. And well, what did that produce? That produced infinity categories with a conservative functor to P. So by that, I mean that this is a full subcategory of infinity categories over, well, let me sort of, to be pedantic, write NP, but I may just write P at some point, over P, such that the structure morphism is conservative. So I'm just gonna write this as STRP and call this the infinity category of P of, let's call it for the moment, abstract P stratified homotopy types. And so in an ideal world, you know, you would want something like this, and you want to be contained in here sort of all differential topological examples, like these topologically stratified spaces of Goretzky-McPherson and Whitney stratified spaces and all of this sort of stuff. And so many people have worked on this. So let me list a few people, and then I'll state the theorem, which is that this thing is actually a reality. So many have worked on this. So probably a pretty early one was Andre Enriquez. Another person who did some work on this was David Miller, sort of working just in the homotopy category. There's a lot of work on this by Ayala, Francis. And then now there are two separate other people, Hiro Tanaka and Nick Rosenblum.
So that's off screen, just to...
Oh. Oh, now I misspelled this. Y-U.
It's still misspelled, but never mind.
Oh. Well, yeah, I'm probably, for some reason, I have a very hard time spelling. I don't know. It's something about not knowing what vowels to pronounce.
I think it's actually right. Is
Yeah,
that
that's right.
what's wrong?
Doesn't he usually have an S in his? Anyway,
No, that's right.
I think it's a Z.
Yeah, David Chateau, Stephen Nantalal, and his advisor, John Wolfe. The student of David Chateau, Sylvain Duteau, sort of really filling in a bunch of details and really making a lot of ideas precise in Andre Enriquez's work. And then lastly, me sort of putting many things together. And so, okay, so I just wanted to give people credit where credit is due. And now let me state the theorem. So first, let me give a bit of notation. So P will be a poset again. And I'm gonna write top over P EX inside of top over P for the full subcategory. Spanned by those objects that the sing P construction actually is an infinity category. So the X just stands for exit path. So spanned by those T over P such that sing P of T is a quasi-category. Okay, and so here's the theorem that sort of realizes in as general a way I could find this stratified homotopy hypothesis. So it's that there's an equivalence of infinity categories. Well, so we're going to start with these guys that the sing P construction actually gives me a quasi-category. Well, it's going to give me one of these, infinity categories with a conservative functor to P, so it's going to land in the guys such that the functor to P is conservative. And well, I'm going to have to invert some class of weak equivalences that I'll tell you what it is. But the theorem is that there's an equivalence after I take these guys for which this construction actually produces a quasi-category, and I invert a class of weak equivalences. So there are two ways that you can identify what this class of weak equivalences is. So the first way is a way that sort of depends on the model in some sense. So it's equivalences say in the Joyal model structure, i.e., because the things will be quasi-categories, fully faithful and essentially surjective functors after taking sing P. So this class W is the class of morphisms that become equivalences of infinity categories after applying this functor that uses the model. So I mean, maybe that's not so satisfying. So here's some model independent way. Or really, I mean, it doesn't, it only uses stuff on this side and it doesn't use any of this thing P stuff. So F from T to T prime in this category is in this class W if and only if the following two conditions are satisfied. So the first one is it's an equivalence on strata. So for all P in P, the induced map on strata is a weak homotopy equivalence. And then you need some data to glue this together. So whenever I have a P less than a Q in P, well, what can I do? I can take the space, and I mean, here I mean like the topological space of sections t over this. So I'm gonna like take a unit interval. I'm gonna stratify it in the usual way, but regard it as, you know, sitting over this p less than q inside the poset, and I'm gonna take sections over that.
You mean the first endpoint, the 0 of the interval goes to p and everything else goes to q.
Yeah, let me actually rename this as p0 is less than p1.
Oh. So
that's better.
So they don't have to be adjacent in the poset in any sense.
No, they don't have to be adjacent in the poset in any sense.
So we could have gone really deep in the stratification here.
Yeah, so you can go really as deep as you want.
Right.
Remember that there are crazy posets out there, like say the real numbers with the usual ordering.
I'd rather not.
So adjacent, but the theorem applies in that generality.
Well, maybe, but I don't know any examples off the top of my head of places stratified by the real numbers, so I'll pass.
In any case, is it right that that you can reduce to adjacent ones when that notion makes sense, like when there's what do I want to say? There exists a maximal factorization of any arrow?
Definitely not.
No.
But still, that doesn't suffice to check adjacent ones.
Sorry, are we requiring P here, P?
That's probably would fail over delta 2,
no,
right?
P has no requirements. So.
Oh, okay. So anything. All right. Thanks.
Yeah. So yeah, maybe I should P any poset. Because I mean, so part of this is that we're not saying that this is equivalent to like, you know, equivalence is checked on exit path categories or something like this. It's somehow it's more general. But in the case where
I'll just jump in to speak to Aaron maybe only. If it need not be the case that exit of x to p is exponential. So in other words, the longer morphisms need not be determined by the shorter morphisms, like the space of longer.
Despite being a left vibration?
It's not a left vibration.
Yeah, I don't.
Yeah, it's not a left vibration.
Sorry. Yeah, that was actually my fundamental confusion. Of course not. Thank you.
Yeah.
So what you're doing is identifying Joyal weak equivalences of the singular construction. That's what the theorem is, main part of the theorem at this moment.
Yeah. So there's there's something to observe. Well, there are a number of things to observe. So the first thing is really, I mean, this theorem doesn't get proven by just somehow doing like, you know, just somehow by hand proving that this thing is an equivalence. So really, this infinity category, you know, this sort of purely categorical thing is a localization of the bigger guy of all topological spaces over P at a class of weak equivalences. But the class isn't very explicit, and on all of this guy, we don't know it is given by this sig P construction. I mean, it doesn't particularly even exactly make sense. But what I mean by this is that, you know, we had this adjunction and we don't know that that's like some Quillen equivalence between, you know, some model structures on both sides. But I'll explain more about this.
So in particular, you're not able to think of either the left or the right as fibrant objects in some.
You are able to think about this. I'll explain this later.
Okay.
But this it becomes a bit more complicated. And so somehow the fundamental issue is exactly
Peter?
this thing. Yeah.
Just to let you know that your document camera's quite a bit laggy behind you.
Oh.
Oh,
okay.
So when you were pointing just now, I didn't see which thing you were pointing at. I don't know if other people are having the same impact, but.
Yeah, that's very good to know. Maybe next time I should try to use the higher quality video on this thing.
Oh,
I'm not sure that will
Maybe
help.
higher frame rate, lower quality.
Yeah, well, I don't know how to adjust.
so
But
let me
anyway.
just say what I'm confused by. That your infinity categories over the nerve of P. That somehow, as a fibrancy condition, I'm finding it rather mixed, because somehow, if that were fibrant objects, then the fibrancy of the infinity categories, and then to think of functors as part of a fibrancy condition, I'm finding a bit
yeah. So
confusing.
I mean, let me now address this actually.
Good. Okay.
So before, yeah, I was going to do this later, but I think it's good to do now. So the observation is actually that this stir P. So remember, this is infinity categories over P, where the structure morphism is conservative. I'll just write it like that. This is the underlying infinity category of a actually simplicial. This part's not so obvious, but it is true. Model category. And what you do is you localize the Joyal model structure on well, so right, whenever you take a slice category of a model category, you get an inherited model structure on the slice category. So you take the Joyal model structure on this slice category, and what does that present? That presents you just infinity categories over the poset. So you take that, and then so you localize this by inverting homotopies respecting stratifications. So, you invert things that look like X cross delta 1 to Y, where this is stratified by projecting and then doing some map of simplicial sets over the nerve of the poset. I mean, there's a different way of saying this, which is just for every element in the poset, yeah, you're inverting the class of morphisms. That's like the inclusions of the endpoint of delta 1 into, yeah, so another way of saying this is that you're inverting the maps that are like this. So for every point of your poset, you have a stratified one simplex that's just mapping down to that point and then, including. And you want to invert the inclusions of the endpoints into here.
Mm-hmm.
Does that make sense?
I'm just wondering if you can get at that by adjoining, I mean, by saying what new trivial cofibrations you have or something like that, or is
yeah,
not...
so
okay. Using what Peter just said, yeah, you can, like,
maybe,
that's a Szyszynski model structure, so you can do that by hand.
Oh, yes, okay.
Yeah, so let me say, so this model structure is studied in detail in, well, let me just say my paper. And it's called, in this paper, the Joyal-Kahn model structure. And I mean, in particular in this paper, you know, I show that it's actually a simplicial model structure. But yeah, this is studied in detail there. So if you're interested in thinking about this infinity category of infinity categories with a conservative functor to P, I mean, there's a lot of stuff that one can say about that that's there. So, I mean, right.
So one thing that you emphasize is that it's a simplicial model structure. So
yeah, yeah.
Are you going to say more about that, or should I ask a question?
Yeah, you should ask a question. I wasn't.
Okay.
Yeah.
So I mean, one thing that's kind of reflective of like the of this fact that we were looking at before, that when you look at functor categories inside here, instead of being categories, they're just infinity groupoids.
Yeah. Yeah, so the mapping spaces between fibrant objects, okay, let me say mapping simplicial sets between fibrant objects are Kahn complexes in particular. So yeah, so if you, yeah, if this other justification wasn't compelling to you, you can read this and see why this is actually a simplicial model structure.
So the fibrant cofibrant objects are just infinity categories with a map to with a conservative functor to NP, right? That's
yeah, exactly. Yeah, so in this model structure, every object is cofibrant. The cofibrations are the monomorphisms.
Oh yeah, an interesting. Oh, sorry. Go ahead. I wanted to say something interesting really quick, was that the Joyal model structure itself is not a simplicial model structure. So
yeah, the Joyal model structure is not simplicial. So yeah, I mean, you're taking a left Gauss field localization of a model structure that's not simplicial. So it's non-obvious that this is simplicial, but it turns out to be. And I mean, if you buy this thing about, you know, if you beforehand believed that, you know, functors over P in this infinity category, you know, aren't actually just form an infinity groupoid, you might be led to believe that this is possible. But yeah, there's a kind of interesting trick to show this is true. Well, I don't know if people have more questions about this, but I wasn't planning on saying a whole lot more about this.
I've got a quick question. So Sing P, how is that related to the exit paths?
Yeah, so I mean,
do they agree like on the nose sometimes, or not necessarily?
Wasn't that the definition?
Yeah, I mean, that's a definition. So
we just write exit for Sing in case that it's a quasi-category.
Yeah. So just when Sing P actually is a quasi-category, which is not always, then I just write exit P, just because I don't know, it's kind of to me, it's a more compelling notation. And
all right, yeah, because I was just asking earlier when I mentioned, do we require P to be Noetherian? You said something about like, we're not saying that this is true for something about exit paths or whatever. I didn't understand that comment.
So I'm saying that I did not say that the weak equivalences were here were the same as equivalences of constructible sheaves in general.
Okay.
If you're in this situation of Lurie's theorem, the classification result, what you might call the exogamy theorem, then what this theorem is saying is that equivalences on exit path categories are the same things as equivalences on constructible sheaves, which are also the same things as equivalences on strata, and these things, which are called links.
Yeah. Okay, thanks.
These guys will come up more soon.
Peter, could you write on the page which part of your paper has the trick that you mentioned?
Oh yeah. So let me, yes, 1 second. Let me open my paper because I think I remember the section number, but let me, I mean, there's only one section that's relevant, but I can tell you even,
No,
yeah.
I'd say the whole paper is relevant, not just one section.
No, yeah, I guess I meant relevant to this trick. Yeah, so the model structure, this is really considered in section 2 of the paper.
Okay.
And section 2.5 is where we complete the proof.
That's the room where it happens. Yeah.
That so simplicial sets over Nerva P in this Joyal-Kahn model structure is simplicial. Yeah, so I mean, it's one of these things where there's a nice criterion that you can check for to check that a model structure is simplicial. That let's see if I, yeah, that I check, and like the thing in this setting that is a little bit hard is that the weak equivalences are stable under filtered colimits. That's one of the things in the criterion that I use to check. That's the thing that's a little bit tricky, but there's a kind of I don't know, when I discovered it, I found it an exceptionally weird trick to do this, which is, I mean, something kind of weird about this model structure is that if you look at objects, right. So if you look at objects with the property that all of their strata are Kahn, but they may not be a quasi-category, just all their strata are Kahn, then the weak equivalences are precisely the Joyal equivalences. So, you know, a priori you have more, but as long as the strata are Kahn, the weak equivalences and the Joyal equivalences coincide. And the Joyal equivalences are stable under filtered colimits. So, I mean, all you need to do if you want to show that the weak equivalences here are stable under filtered colimits is find some way of replacing an arbitrary object by a weakly equivalent one. You know, a functorial way of doing that such that functor preserves weak equivalences and the fibers are Kahn, and then you're done by this Joyal thing. So you don't even have to replace it by a fibrant object. You can just replace it by some junk where all the fibers are Kahn, and you can just do this by hand by basically fiber-wise taking EX infinity. But yeah, it's some weird non-fibrant replacement thing. Anyway.
Interesting. I see.
Yeah, so that's done in section 2.5.
So the key, okay, so I can say in summary that the key idea is somehow that you can invent a relative fibrant completion construction and then take it from there.
Yeah, though it's kind of weird because the thing that I do isn't even a fibrant
No.
completion.
I got it.
Yeah.
But it's the functor which rules the situation, let's say.
Yeah.
And becomes fibrant completion when P is trivial.
Yeah, it becomes fibrant completion when P is trivial. Yeah, so the other thing is this model structure when P is trivial or when P is discrete, it coincides with the Kahn model structure. So that's part of why I called it by the theorem. So that's part of why I called it the Joyal-Kahn model structure, is because it it kind of mixes these two. The fibers are sort of Kahn, but then globally the things are quasi-categories.
Yeah, this conservative condition is clearly, it's preventing all the pathologies which you might fear somehow.
Yeah. So it's a lot better behaved in some ways. I mean, there are still parts of it that are not, you can't really say completely, like you can't, or I at least do not know, how to characterize completely fibrations between arbitrary objects in this model structure, for example.
I see. But is there an analog of minimal objects in this category?
Minimal objects.
And like minimal complexes, minimal fibrations, that world.
Oh.
Yeah.
I think
I don't
a minimal
know.
quasi-category
Skeleton.
will automatically.
Yeah,
there's
good point.
Yeah,
so
I think
if we
that you
take the
just do
minimal
that.
quasi-category, it will be
Right. It will be such a thing.
It'll still be in this category. That preserves conservation.
Yeah, that's
Certainly.
a good point.
Yeah.
Yes.
Yeah. Also, this property where you can't characterize all the fibrations between non-fibrant objects is like true already in the Joyal model structure. So that's not so bad.
Yeah, exactly.
So I'm going to throw out there that it might be quite possible to simply write down all minimal objects in this category.
Yeah, I mean, it might very well be. Yeah, I don't know. So I mean, so okay, let me. Are there any more questions on this though? Before I say some other things, I'm gonna sort of return back to this, but I want to say a few other things first, and then I want to give a sort of broad overview of the proof of this theorem. So, and maybe I should emphasize, so for us, sort of what happened is that Clark and I and Saul Glassman wrote this paper, and we had wanted to prove this theorem sort of earlier as a justification for what we were doing in the paper. Somehow that in the algebra geometric setting, these sorts of topological spaces, with this such that Sing P is the exit, it is actually a quasi-category. In algebraic geometry, topological spaces are, somehow not well behaved in this sort of conically stratified. So we actually just kind of worked completely in here. And originally we thought, oh, we were going to need this. And then we realized that we could just work completely in here. And then, but we still wanted a justification that these are really the same and that you could get examples of things like Whitney stratified spaces or any conically stratified space in here. But it turns out to be a bit more difficult, to show this than sort of the, classical sort of equivalence of homotopy theory between simplicial sets and topological spaces. And somehow the fundamental reason is you don't even know how to vibrantly replace something here, because, there's basically like one condition that you have to check that Sing P of something is a quasi-category, and it's this conical thing. And it's not clear how to just take some arbitrary topological space and replace it with a weakly equivalent conically stratified one, partially because weak equivalences in the Joyal model structure between non-fibrant objects are, just completely intractable, basically. so I want to, before going on to more sort of details of the proof of this, I want to talk about a little bit of relation to other work.
Peter, just to ask, so
Yeah.
do you have, like, let's say that I chose my favorite infinity category with a conservative functor to my favorite poset.
Yes.
Do you have something that says, you know, on the level of object, like, oh, always I can realize it by, so I understand you can always realize by the topological space, by what you are told, but by something, you know, nicer, like by something which is maybe a manifold or you know, stratified manifold, or like, how good is the reconstruction situation?
Yeah, so I mean, yeah, I don't have a very good reconstruction. I think in a more restrictive setting, maybe David and John and Nick have a bit of a better, or certainly a better idea of reconstruction than I do. But I mean, in general, I don't really have like I haven't really thought too much about this either. So let me just say that. Yeah, so sorry, that's not a very satisfying answer.
No, that's okay, thanks.
I think that's tough. Like the right cone on a space, it is hard to see happen in terms of a nice topological space. Like that cone point needs to be represented by a contractible space.
Yeah.
And
yeah.
And if you want all the kind of nice conically stratified features to be possessed, that link needs to be really high dimensional. I don't know. It doesn't seem to be an easy thing to answer through any kind of method.
Yeah, no, it seems, this seems very, very difficult.
Somehow you always know what to do if you've got a small enough poset. I wonder if, I don't know, I've been wondering about this exact issue.
Like the orbit category of a finite group.
Yeah, exactly.
Yeah. This is,
It's a relevant example.
No, yeah, I've really been wondering about this too. It's, I don't know, if there's something, there's something about this that's difficult in general. Yeah. But okay, are there any other comments or questions? Okay, so let me before discussing the proof, I want to say just a slight bit of a maybe prelude to what David will talk about, or a very tiny amount of what David will talk about on Friday. So so here's some little bit on some relation to other work. And so David, John Francis, and then I guess, well, I'll do this weird thing, Hiro Tanaka and Nick Rosenblum, they define a notion of a conically smooth atlas on a P stratified space. And let's see, David, am I right that this poset should be down finite? That the sort of posets appearing in your stuff are down finite?
The posets appearing have the property that they're down finite, yes.
Yeah, so these will,
but yeah.
Yeah. So I mean, very roughly, this is some atlas where you have sort of covers that are by some copy of a Euclidean space crossed a cone on some conically smooth stratified space of something that's strictly less depth. So this is a sort of inductive definition. And I mean, I'm not going to say really more about this. So this is defined inductively on the depth, say, and then plus there are a bunch of conditions that have to do with some regularity things. And so the point is that these are sort of like the good notion of sort of smooth object, like sort of smooth manifolds in the stratified setting. So their strata are smooth. So when the poset is the point, this is the structure of a smooth manifold. And generally the strata are smooth manifold. And so I'm going to write, so I think, I'll ask David if this is correct. So, I mean, you sort of work with all the stratifying posets sort of all at once, but if I fix a poset, so I'll write con P for the category of conically smooth P stratified spaces. So I'm just going to fix a particular poset just for sort of convenience of presentation. And so the theorem, or well, one of very many theorems that ILF Francis Rosenblum proved that's in this direction is that taking exit paths, this defines a fully faithful functor. So you take these conically stratified spaces and you invert a class of equivalences. And so what are these guys? These are really stratified homotopies. Using the real line as your homotopy. So it's a much sort of stronger class of weak equivalences than the thing that I was talking about earlier. So they show that if you start with this sort of stratified manifold setting and you invert the actual homotopies, then this embeds you into infinity categories with a conservative functor to P, this stir P. And so so then the sort of observation, so maybe I'll do this in red actually. So here's an observation is if we look at this this category of topological P stratified topological spaces where the Sing P construction is a quasi category, and we invert this bigger class of weak equivalences. Well, by the theorem that I said before, this exit path construction is an equivalence here. Now, there's actually a forgetful functor from here to here that forgets the atlas. So this was a structure, conical smoothness was a structure on a stratified space, and you can forget the structure. But if you forget the structure, you're still conically stratified. It's part of the definition. And this class H gets sent to, oh, I think my headphone may have cut off. Can you all still hear me?
Now I can, yeah.
Okay,
yes,
sorry, I think my headphone died.
The
So,
sound actually got clearer for a moment there, or like louder.
oh, it may have been, I think
Maybe it
if
jumped to
it's
your
using
computer
my
or something.
computer mic, it's louder,
Yeah.
but then it also creates a lot of sound in my house, so
Okay.
I use the headphone.
Oh yeah, you don't
okay.
want to wake up your roommates.
Yeah, well, and then they may be able to hear jokes like that, so it's better. Well, okay, I should remember that this is being recorded. So anyway, so you can forget the conically smooth structure. And so since this is fully faithful and that's an equivalence, this is also fully faithful. So as a homotopy theory, this embeds into here. However, I mean, you know, from my understanding, part of the reason of working with this is so that you can talk about factorization homology of stratified spaces before, you know, inverting homotopies. And I mean, you can't do that here. You need like some manifold type structures to do that. So this completely cannot do that. But if you invert these stratified homotopies, you embed into this category here. And I mean, of course, for that, you only needed that this is fully faithful, which is an easier result than showing that this is an equivalence. As it turns out, that's not too bad, but the equivalence part, you need to check some stuff. So I just wanted to say that, but you know, I'm certainly not an expert on conical smoothness, but I'm excited on Friday to learn more about this.
Do we know anything about the essential image?
I think, David, do you have a conjecture about this in your paper?
Oh, if I do, I forgot it. I don't have any thoughts right now about it.
Yeah, I mean, so I think I remember some conjecture about some sort of finiteness, you know, properties of the infinity categories here. So I don't remember specifically, but I guess like, you know, if you take the things that are just stratified over a point, they're smooth manifolds, right? So you want to know like what the underlying homotopy types of smooth manifolds are. And then you would want to know, well, where do they come from? So, so maybe let me ask one question. So at least in the published version of this paper, one thing that is a conjecture is whether or not Whitney stratified spaces admit conically smooth structures. I don't know if you have any thoughts of this, more thoughts on this, David, but.
Yeah, so it's still outstanding, I suppose. I mean, example at a time. There's a large class of Whitney stratified spaces that are conically smooth. But at the level of the generality of just given a Whitney stratified space, is it conically smooth? I don't know the answer. I don't think anyone has thought about it very hard.
Yeah, probably. Yeah, I mean, I certainly haven't. But yeah, so I guess one, you know, so yeah, there's a conjecture as to whether or not, you know, all these live in here. You know, it seems, I mean, to me, like probably yes, but maybe one certain pleasant feature about this, if you don't already know that, is that they do all live in here. So this shows that, you know, somehow, and all topologically stratified spaces and all conically stratified spaces live in here. So it gives you a, you know, a large class of examples. But I mean, they're, you know, kind of only for homotopy theoretic purposes. You can't do any manifoldy things, you know, in here because you don't have that structure. So you can't talk about factorization homology here, which, you know, is something you would like to do. So, but I just wanted to say about that relation. Are there any questions about this?
I'll just make a quick comment that so I need to get going soon, and then at 10 a.m. is MSRI's virtual seminar. So I just want to let that be known.
Yeah, that's a good point.
Yeah.
Yeah.
Okay. So, yeah. Okay. So now I'll give a bit of a quick overview of how the proof of this theorem works. This equivalence of homotopy theories between p-stratified topological spaces, and then this just purely, you know, categorical thing. And this is going to be one of the key observations, is this sort of characterization of the equivalences. But let me first say.
I just realized I have a question. I don't know if
Yes.
you'll know the answer to this off the top of your head, Peter, but in con P8 with H inverted, what's the correct way to ask the question? Are the homotopy equivalences, maybe I actually know the answer to this. Are the homotopy equivalences like saturated or something? That is, if I've got an equivalence, what am I trying to say? If I've got a map of conically smooth things that gives me an equivalence in the infinity category, was it necessarily a homotopy equivalence? I just realized I didn't know off the top of my head.
I think, okay, yeah, so I think, so sort of a posteriori after this theorem, I think this has to be true. Let's see.
It has to be true? How come?
Maybe not. So, let's see. Well, I guess, yeah, what happens? So, I mean, you know that this is fully faithful.
Right, but that doesn't, I mean, I guess my question is entirely internal to con P. Like we know that a map of, right, we know that if a map is we know that the weak equivalences in your top X are whatever the word is. What is the word?
Saturated?
Saturated, thank you, Tomer.
Saturated.
Saturated. But I guess I don't know that for I personally don't know that for con P.
Yeah, maybe.
Is it clear?
I think it's true.
You think it's true?
But I haven't thought about the question, but I think it's true because if you have two
Yeah.
that are equivalent in the infinity category, that can be represented by a zigzag, these suckers, but each zig and zag is itself represented by an arrow in either direction. I don't know. Just so I think that you could just, for the same reason that you know it's true for topological spaces, quote, inverting homotopy equivalences. I think you could just repeat that rationale. But
Okay.
Yeah. Yeah, and I guess, right, maybe just to, reiterate something, right, like in the, okay, if you think very loosely about this, it seems quite believable, like, it sort of, stratum-wise, if you have a weak equivalence of manifolds, right, you can always represent that by a homotopy equivalence. I mean, you need to, of course, glue these together, but I don't know, it seems quite believable to me, though. Yeah.
Yeah, it just occurred to me that I didn't know that off the top of my head.
I have another small question related to this, somehow the relationship to the differential story. So in the case, the non-stratified case, you have an interesting relationship between homotopy and infinite dimensional differential topology, right? Like infinite dimensional manifolds are essentially, they're homeomorphic if they have the same homotopy type, essentially. Do you know if there's something like that in the stratified sense? If you work with infinite dimensional manifolds, then somehow the theory collapses to the homotopy?
I don't know. I would ask David. I mean, yeah.
David?
Well, so obviously I don't know. That's an interesting question. My instinct is that the answer would be yes, but it would bootstrap off of the logic that you already know for smooth manifolds in the unstratified setting because essentially a stratified space with any adjectives is a presheaf on the subdivision of its stratifying poset. And so in the conically smooth setting, that presheaf takes values in smooth manifolds, essentially, or bundle, or in a certain sense. And then you can just point-wise do the trick that you mentioned, like value-wise. That's my instinct.
That's cool. Thanks.
Yeah. So actually, I mean, what David just said is a pretty good segue into what I'm about to say next. So, okay. So here's the proof. Yeah. Here's the proof overview. So, okay, let me just say something that doesn't work first, because this is something I tried for a long time and it didn't work. Well, I don't know how to make it work. So, okay, we're in a pretty good setup to do this. So your first try for proving this theorem is to transfer, I guess I should say transfer what I call the Joyal-Kahn model structure on simplicial sets over nerve of P to topological spaces over P via the adjunction that we've been considering, this sort of stratified realization and sing P. So you might try to, transfer this model structure. So I mean, the first thing, maybe the first thing to say is that, I mean, somehow there didn't really exist already a homotopy theory of p-stratified topological spaces, in this sort of generality. So you might try to define one. I mean, if you think about how Quillen, proved that simplicial sets and topological spaces and the classical model structures are Quillen equivalent, well, he defined the model structure on simplicial set, then transferred it, and then proved that they're equivalent. Because once you've transferred it, you don't have to check too much to show that you get an equivalence. So so you might try to transfer and show the resulting Quillen adjunction is a Quillen equivalence. But basically this doesn't seem to be possible. And I mean, for some of the reasons that I said before, I mean, generally, the Sing-P thing isn't a quasi-category. That was something that you had available in the, unstratified version. Sing is always a Kahn complex. Also, I mean, you just don't know what Joyal equivalences between arbitrary simplicial sets are. So I don't know. Many people have tried to do this sort of thing. So some other people besides me who tried to do this are Stephen Nantlal and John Wolfe, for example. But I mean, I don't know, it seems quite difficult to do this. And Stephen's thesis is really nice, and he outlines in a section like a ton of reasons why this seems very, very difficult to do. So the comparison.
Sorry, Peter?
Yeah.
Didn't Sylvain Dotto also try to do this, or am I misremembering?
I don't think, well, I guess he kind of tried to do it. Yeah, I'll add him to the list. Though, I mean, he ultimately did the other thing that I'm about to talk about. So the comparison will be indirect using a what you might call a Siegel space model. And this is this thing that David was mentioning before. So this is what we call decollages, meaning ungluings. So the observation is that a morphism F from C to D in this infinity category of infinity categories with a conservative functor to P, this is an equivalence if and only if the following two conditions are satisfied. So essentially it's this, how I identified this class W before. So for every P in the post set, the induced map on the Pth strata, so I just mean the pullback of infinity categories, is an equivalence in the infinity category of spaces, because these strata are infinity groupoids. And then the second thing is for all P less than Q in P, this same sort of condition. So if I take maps over P from the post set P is less than Q, sitting over P and in the usual way from C, and I do this for D, that this is an equivalence. So the point is that this part guarantees essential surjectivity and full faithfulness for objects in the same strata. And this part guarantees full faithfulness for objects in different strata. I mean, something else to notice is that this Pth stratum is also known as sections over the point little p of the map from C to big P. So what's the point is that the sort of, maybe let me say it this way, restricted Uneta functor from here to functors from linearly ordered subsets sigma of P with cardinality equal to 0 or 1 to spaces. This is conservative. And there's a fix to make it fully faithful, which is that you enlarge this to the whole subdivision. So what do I mean by that? So here's some notation. So write SD of P for the post set of linearly ordered, I guess I should say non-empty, finite subsets of P ordered by inclusion. And note, there's a nerve functor it's just this sort of restricted uneta thing from here to pre-sheaves on the subdivision of P, sending C over P to the functor that sends a linearly ordered finite subset sigma to maps over P from sigma to C. So it's sections over sigma. Okay. And the point is that the functor, this nerve functor right here, is fully faithful with essential image those pre-sheaves such that the following condition is satisfied. So for all linearly ordered finite subsets in P, the map, well, I can take the value of F on this linearly ordered finite subset, and that has a map to the value of each of the sort of consecutive pieces crossed over the next part. Da, da, da. So that this Siegel map is an equivalence. Okay. And so this expresses stir P as, well, so as a localization, but the localization commutes with filtered colimits because finite limits commute with filtered colimits in the infinity category spaces. So it's an omega accessible localization of these pre-sheaves. And we call the objects of the essential image décollages. Because they're sort of ungluing your stratified space. Okay.
So I should mention, since David Ayala isn't here, I should mention that he cooked up exactly the same definition independently of us. So.
Yeah, for sure. Okay, so what's the game? The game is going to be compare. Now we want to compare things to this setting. And okay, so like, what do we need to do? We have some sort of category of topological spaces. We first want to, define, some homotopy theory on some model structure or something. And then, we want to show that it's equivalent, it's equivalent to the thing that we sort of abstractly thought was the right homotopy theory. But somehow the point of this is that this structure is a bit more flexible for doing that. So now what I want to talk about is what I call the Duteau Enriquez model structure. So, I mean, the thing to notice is that, right, pre-sheaves, if you think about the model categorically, you can think about them as, pre-sheaves of simplicial sets in the projective model structure, and then you can localize further. So let's first just try to do something with pre-sheaves and localize. So the observation is that we have adjunctions between simplicial pre-sheaves on the subdivision of a poset. I won't name this functor. This one I'll also call NP. Simplicial sets over the poset P. This is going to be the adjunction we've been thinking about. Topological spaces over P. So, I mean, this is defined basically in exactly the same way as the NP before. So if you look at what this composite is, what it does is it sends some linearly ordered finite subset sigma to sing of the topological space of maps over P from the realization of this guy to your topological space T. Okay. And the game that you want to play is you have the projective model structure on here. This isn't what you want in the end because you want to enforce the Siegel condition, but maybe you can first just transfer that over here and then prove, well, basically, the above result is showing that this, you can promote this to an equivalence between this Joyal-Kahn model structure and a localization of the projective model structure here. So you want to sort of prove that the long thing is an equivalence and that, yeah. But then this thing I won't know its equivalent adjunction, but that's okay. So that's the theorem of Sylvain Duteau after Andre Enriquez. So Andre wrote this note and I mean, had almost, had things very close to being there, but not quite. And I had looked at this and I couldn't understand basically one part of the argument. And, I had talked about this with Sylvain a bit and had sent him this. And then a couple of years later, or a year and a half later, he figured out how to unravel the argument. And in the appendix of my paper, there's a simplified and slightly strengthened version of what Sylvain proved in his thesis. But so the theorem is that the projective model structure on this pre-sheaf category it right transfers to topological spaces over P. So that means that I'm going to say that something's a weak equivalence or fibration here if it is after applying this functor. And then the cofibrations are what they have to be. And part of that is that actually defines a model structure along that above adjunction. And then moreover, the resulting Quillen adjunction, which I'll just write as that, is a Quillen equivalence. So what does this tell you? I mean, this tells you that you have, you now have some model structure here that you know is equivalent to gives the underlying infinity category pre-sheaves of spaces on here, and you know that the thing you want is a localization of both, so you can invert some more equivalences. But part of the difficulty is that there's not good properness in this side, so you don't actually know you get a model structure in the end. You only get a semi-model structure. Yeah, and I should say it's a Quillen equivalence of a combinatorial simplicial model categories. And how this gets proven is first you use a transfer argument. That's a transfer argument of that. I mean, it's like, from my perspective, it's like the most useful transfer argument of Catherine Hess, Magdalena Kadzoriak, Emily Reel, and Brooke Shipley. So you use this transfer argument, and actually what you do is this adjunction here, it factors through an adjunction between topological spaces over the realization of the nerve of the poset. There's a forgetful functor, and topological spaces over the poset. This one is the pullback functor. And what happens is, yeah, this factors through here, and you actually transfer to both here and here. Then the fact that this is an equivalence ends up following from the fact that if you take the exit path category of the realization of the nerve of a poset, mapping to the nerve of the poset, that this is an equivalence of infinity categories. So that's where you get the equivalence here. And then this ends up being what the model structure is here is some very rigid thing. It's like some version of stratified spaces where if the poset is 0 is less than 1, this guy's the interval. And you're thinking about spaces over the interval. But the sort of how the stratifications have to work is if you add an exit path, it has to lie exactly over every point of the interval it was on. So it's much more rigid. And then you prove that the resulting Quillen adjunction between these two are equivalences. And that is, by some topological argument. You have to do something with point set topology. Okay, so to complete the proof of the theorem that I stated earlier, you need to check.
I wonder if you could do this next time, because we just have a minute till the seminar.
Yeah, this will take 1 minute.
Oh, okay, sorry.
So, and this is it. Yeah, so you need to check that for a map in between guys such that their Sing P is a quasi-category, the Dutot-Enriquez equivalences are the same thing as equivalences after doing Sing P. And the second thing, that part's easy. You need to check by hand that, well, now by 1, you know quasi-category, and you invert the Sing P equivalences, then you know this embeds you into here, and you need to check this is essentially surjective.
Mm-hmm.
So this is one of the things that I do in this paper is you need to check this by hand. And essentially what it amounts to is you pass through another, sort of zigzag, and you reformulate various things, and then you arrive at the statement not being too hard. But you have to pass through a third model of things. Maybe let me not talk about that.
All right. Well, I'm sure people are going to be scurrying off pretty quickly, but thank you, Peter.